Hello everyone, this is your teacher Craig, and today I'm going to run through some problems that are a lot like the mastery exercise problems from Mod 6. Many of us had a tough time with this set or are having a tough time, and I thought I'd run through some problems that are very similar to the ones that you're doing. Let's jump in. First of all, here's one about one of those card problems. We see quite a few of these. If you are dealt 3 cards, not 5 cards, only 3 cards this time. If you are dealt 3 cards from a shuffled deck of 52 cards, find the probability of getting 2 jacks and a queen. Okay, so let's make sure got things down here. We got 3 cards, not 5. And let's see, we're looking for 2 jacks and 1 queen. Okay, in just about every probability problem I do, I like to think of this definition of probability, which says the probability of some event is equal to the number of favorable outcomes, or the type of outcomes you're looking for, over the total possible number of outcomes. Now, this looks more like theoretical probability than empirical probability to me, or maybe it's a little bit of both. I'm not exactly sure, but they're so similar that I just use this one all the time. Okay, so let's see. To do this problem, first of all, the denominator is the easy part. Total possible outcomes. Well, let's see. We're dealt 3 cards from a deck of 52. Let's see, we're dealing with cards. Does order matter? Let's see, does it matter if you get a 10, then a 7, then a jack, or a jack, then a 10, then a 7? No, it doesn't matter in cards. And so we could say that is a combination. And we've got 52 cards. And this is a combination, and we're getting 3. That's how many total possible outcomes there are. But how many favorable outcomes? Well, it turns out this numerator is an example of the FCP. And what we're putting in both of these blanks for the fundamental counting principle is the number of ways to get our 2 jacks. I didn't leave enough space. Number ways to get 2 jacks times the number of ways to get 1 queen. Okay, so how do we do that? Well, let's see. Jacks. We're looking for jacks. How many? We don't need to consider any of the other cards initially here because we're only looking at getting jacks. And so we only have to think about the 4 jacks that are in a deck. Well, how many ways are there to get 2 of them? Again, is it a permutation or a combination? This is another combination. Again, we're dealing cards, and it doesn't matter if you get the Jack of Hearts and then the Jack of Diamonds, or you turn it around and you get the Jack of Diamonds and then the Jack of Hearts. Order doesn't matter. So for this first slot, it's a combination. There are 4 jacks, and we want the number of ways to select 2. Likewise, for the queens, we will do the same thing. There's 4 queens, and we're looking for the combinations that'll get us 1 queen. Okay, so let's see. This is, well, I'll just rewrite this here. 52 combo 3. Note that the 2 plus 1 makes the 3 cards that we're receiving in our hand. Yeah, it makes sense. We said 2 jacks, 1 queen. All right, so now let's put the numbers in. I ran these already, and 4 combinations select 2. There are 6 ways to do that. And I know if you've got 4 cards and making groups of 1, well, there's 4 of them. And 52 select 3, that's 22,100. And so our probability when we do that math is 0.00109. And again, if you want to put that in percent, I don't recall which way our ME problems ask us to do it, but let's see, I'm going to go 2 decimal places to the right. That means that is 0.109%. Pretty low likelihood. Yeah, let's see, we had 3 cards and the probability of getting 2 of the 3 jacks and then a queen. Yeah, that's pretty low probability. All right, let's move on. Next problem is one that is similar. In this one, we've got, oh, not 3 cards this time, but now we've got 5 cards. 5 cards. Now we're playing poker. What's the probability of being dealt exactly 2 8s and no kings? It sounds similar, and it is similar. Again, we're going to be looking for the number of ways to get what? 2 8s. We'll multiply that, 2 8s, times the number of ways to get no kings. And we'll divide that by the total number of possibilities. Let's see, we're doing 5-card poker. Let's see, we assume it's a deck of 52. So how many ways are down here? Oh, that's 52. A combo, again, it's a combo. It doesn't matter what order we get our cards in playing any card game. Well, maybe some, but not 5-card draw poker. 5 cards. This is that 2.5 million or something like that number. I remember that one. All right, so again, how many ways are there to get 2 8s? Well, that's pretty straightforward. It's a combination. We've got 4 8s to choose from, and we're looking for combinations of 2. How about the other one? Well, we got to do some work here. Oh, let me back up 1 second to the first problem. Yeah, we're okay, but this one has a little bit of a twist. Okay, how many cards are not kings? Let's go over here and figure this out. Not kings. Well, we've got 2 through 10. Those are not kings. We've got the aces. We've got jacks. We've got queens, and we're skipping the kings. So how many cards is that? 2 through 10 makes, is that 8, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 9 cards. 10, 11, 12. 12 cards. 12 faces. Whatever. But we got to remember we got 4 of each. And so we've got 12 faces times 4 of each. We've got 48 cards that are not kings. All right. So it would seem that the way to select our no kings is, let's see, we did 2 8s, which means we need 3 no king cards. Am I right on that? Yes. But there's one other trick, and here's the one that you might be missing. Included in this 2 through 10 is the number 8. But we've already dealt with the 8s. So we need to remove the 8s from our group. So I'll say remove 8s. And there's 4 of them. And so we don't have 48 cards. We have 44 not king cards to choose from. All right. So again, it's a combination. We've got 44 and we're choosing, let's see, 3 of them. Yep. And again, we've got this 52 combo, select 5. Now I can put some numbers down. Let's see if I wrote those down. I did. This is 6. 44 combo 3 is 13 to 44. If I did my math work right. Wouldn't be surprised if there's an error or two in here today. And I'm not going to write down that big number. Which reminds me, I sensed that some of you were having some issues with these big numbers in your calculator. Well, yes, and it's a little bit of a trick. Here's what I do. I type 6 times 13,244, and then I don't hit equal, I hit divided by. And then my calculator, to put this in, I put 52, second combination 5, and when I hit equal, it does the whole thing. Because writing down some of these big monster numbers is kind of tricky, kind of a hassle, but you don't need to do it. You can do the goal, or I should say a wonderful thing to be able to do is to be able to do all the work in your calculator without having to write down all the numbers, all the intermediate ones. Because as you recall, when we start writing down intermediate numbers, if we do rounding of those decimal places, that's when we get into trouble and we're off by, well, let's see, in consumer math, we were off by 22 cents or $4.03, and that made our problem wrong and we weren't happy. Okay, what's my answer here? Find my problem. There it is. This is equal to 0.0306, which moved 2 decimal places to the right. Looks like it's 3.6% probability of being dealt 2 8s and no kings in a poker hand. Pretty small. That pair of cards is tricky. And then getting everything but kings, that adds another element. That's our probability. All right, next problem. We're up to those birthday problems. I posted a update about this, and I'd like to go through it because some of us still had problems with these. It turns out that there's some equations that I determined what they were. I Googled it is all I did. That determine how to solve these when they're a little bit more complicated. And here, the first one is the probability that no one has the same birthday in a group of size n. So for example, if you had 10 people, we're calculating the probability that no one has a birthday out of 10 people. We can calculate that by doing the permutation of 365, select, in our example, 10, divided by 365 raised to the 10th power. Again, n is the size of the group. We can also calculate the inverse of this. What is it? We'll use the complement property of probabilities. We just take 1 minus, here's the same expression in both of these. We'll take 1 minus that and figure out the inverse of this. This is that no one has the same birthday, and here's that at least 2 people have the same birthday in a group of size n. We can't do at least 3 people or at least 4 people. That's a more difficult calculation, and we're not ever asked that. We're simply asked that at least 2 people have the same birthday in the group of size n. So as long as they give us the group size, and they do in every problem, we can solve these problems using these equations. But I'm also going to show you another way. Here's a problem. If 2 people are selected at random, there's our 2 people again, always 2 people, what's the probability that they do not have the same birthday? Same birthday. Let's see, which one is that? Do not have the same, that no one has the same birthday. Yeah, we're looking at this equation. But let's think about this a little differently. First of all, let's think about this as an FCP problem. What we want to do is determine the number of ways that the first person can have a birthday, and we'll multiply that by the number of ways that the second person can have a birthday. Don't forget our friend the FCP. It comes in handy a lot when you have 2 distinct tasks drawing from different populations, we often say. And we're talking about two different things, the first person and the second. If we know how many ways we can do the first and how many ways we can do the second, and if there's the third, the number of ways we can do the third, we just multiply them all together. All right, so let's see. How many ways can the first person have a birthday? Well, it turns out that the person can choose any one of the 365 days of the year. They can choose 365 of the 365 days there are. That's how many ways. What about the second person? Well, since one day is already gone, they can only choose 364 ways out of 365. And this equals 0.9973, or 99.73% chance. It's a very high probability that if you just select two people at random and ask them if they have the same birthday, very high probability you're going to find no, they do not have the same birthday. They do not have the same birthday. Okay, we haven't used our equations yet, but that's coming. I just wanted to show another alternative way of using the FCP here. Okay. Here we go. Here's another birthday problem. 3 people are selected at random. So now we have an n of 3. In the prior problem, n was 2. Now we have 3 people. Now, let's see. Let's use our equation this time. Probability that they all have different birthdays. Well, that's no one has the same birthday. There's our equation. The probability of this event happening is equal to 365 permutation select 3, because n has 3, divided by 365 raised to the third power. Now, these numbers are some of those numbers that are really large. And I never looked at them in my calculator. I never wrote them down. I just did 365 P3. And that's a big number. Oh, I'm going to actually do it. 365 second permutation 3. I get 48,222,180. I could write it down, but I'm not going to, because I'm just going to hit my divide by key and say 365 raised to the third power equals. And it gave me my probability. I didn't have to write down any intermediate number. If you do, you do, but some of these numbers get very monstrous, especially the one we're going to do after this. Okay, so the probability that we got 3 people, and they all have different birthdays, which means no one has the same birthday, is 0.9918. Or 99.18%. Let's see, this should be a little bit higher probability than the prior problem, was it? Yeah, that was 99.73 that no one had the same birthday when there's 2 people. But when you're asking 3 people if they have the same birthday, it's just slightly higher. You're still very unlikely in a group of 3 people to find someone with the same birthday. All right, another boring birthday problem. Here we go. Now we got 5 people selected at random. Find the probability that at least 2 have the same birthday. Oh, we've flipped things around. 2 people have the same birthday. Now we're going to use our complement formula to find out what's the probability that 2 have the same birthday. Okay, we can do that. Let's see, n is 5. We said 5 people. So we've got 1 minus 365 permutation 5 over 365 raised to the 5th. And I did this math. Where is it? Problem number 5. Here we go. That is 1 minus 0.9729. And that equals 0.0271 or 2.71% chance that those 5 people you gathered up randomly, there's almost a 3% chance that 2 of them have the same birthday. All right. Another birthday problem. Last one. Now, I know some of you saw a problem, maybe all of you did, that said something about showing that if there's 23 people in the room, there'll be at least a 50% chance, or a greater than 50% chance that 2 of them have the same birthday. So I kind of turned it around, but let's look at it. If 23 people are selected at random, find the probability that at least 2 of them have the same birthday. Well, same birthday. Let's see. People have the same birthday. That's this formula. So Anna's 23 this time. And the probability of this event occurring 23 people is 1 minus 365 permutation 23 and 365 raised to the 23rd. That is a monstrous number. Yep. Some of you are going to experience scientific notation in your calculator. Let's see, I'm going to punch that one in. 365, raise that to the, 23rd. It says this denominator here, my calculator shows 8.56, then it gives a bunch more digits, and then there's a space, and then it says 58. Some of the others of you might see 10 to the 58. Or some of the others of you on your calculators might see E58, which stands for exponent. But this is scientific notation, and this means 8.56 and all those other digits times 10 to the 58th power. That's a monstrous number. It's taking this decimal point and moving it 58 places to the right. Yeah, that's a big number. Which is why I never write down these big things. I just try to do all the work I can in my calculator. All right, so 365 P23. Where's my answer? I get 1 minus 0.4927. Which equals 0.5073. Which means this is a percent of 50.73%, which means there's greater than a 50% chance that if you put 23 people in a room, you can find 2 of them with the same birthday, which is kind of astounding, but it's true. And we just showed it with probability. How exciting. Math. I bet you guys are just as excited as I am, aren't you? Sure you are. Okay, let's move on. Here we go. Oh yeah, this one caused lots of problems. The probabilities and gain or loss for guessing on a standardized test is shown in the table to the right. So let's just stop there. We're taking a test, and we're talking about a problem that you have no clue what the answer is. All right? And if you had no clue, the probability of guessing correctly, if there's 6 answers, is 1/6. And the probability of guessing incorrectly is 5/6. Again, you have no clue on this problem. And there's 6 answers. It must be multiple choice. Probability, theoretical probability, tells us you have a 1 in 6 chance, or a 1/6 probability of guessing correctly, and 5/6 probability of guessing wrong. Again, number of favorable outcomes over the total number of outcomes. All right, in these standardized tests, they often do this. If you get a problem correct, you get the full point. But if you guess incorrectly, they subtract some fraction of a point. Yes, they did here, which makes you wonder, gee, should I guess on this problem or not? Do I have a pretty good idea what's right, or should I take a chance on losing a quarter point? Well, okay, so that's our setup. But now there's a little bit more. It says on this particular problem, you can eliminate 2 of the 6 questions. Because you looked at them and 2 of them are just stupid answers. They were just meant to throw you off. You know that 2 of these problems are wrong, which means the probabilities change. You're no longer guessing at 6 answers, you're only guessing at 4. So what's the probability of guessing correct? It's no longer 1 over 6. It's 1 over 4. And the probability of guessing incorrect is no longer 5/6. It's the complement of 1/4. It's 3/4. Messed that one up good. Yeah, that's what it is. Again, we eliminated 2 of the problem, 2 of the 6 answers, which means there's now only 4, and theoretical probability says we have a 1 in 4 chance of guessing properly. 3 out of 4 chance. 3 divided by 4 chance, a 75% chance of guessing incorrectly. Now we can do the problem. Okay, what they want us to calculate is modify the probabilities. That's what we just did. And calculate the expected value of the point score on the problem. What is this expected value? Well, it's another probability type concept. And it says if we know the outcomes and the probabilities, we can find the expected value, or what on average you might hope to get, by multiplying and summing. That symbol is sigma. It means sum them up. We will sum all of the outcomes times their probabilities. Probabilities. And I probably should have put a little n equals 1 to n equals whatever. Yeah, whatever. It says we take and sum each of these outcomes times probabilities. So here's how we do it in this problem. Let's see, the outcome, we're going to gain 1 point, and its probability is 1/4. That's those 2. That's if we guess correctly. But then we got this incorrect guess, so we're going to subtract because it's a negative 1/4. And let's see, minus its outcome is 1/4, and its probability is 3/4. Some of us weren't sure about this minus sign, but when we're losing something, we're losing money in the stock market or on the sale of something, we subtract that one. Okay, this gives us 1/4 minus 3/16, right? Multiplication of fractions, just multiply the numerators, multiply the denominators. And 1/4 is 4/16 minus 3/16, or you could have just plugged these into your calculator at any point. Gives 1/16, and I happen to know that fraction. Whoopsie, this was supposed to be a negative 1/16. Whoopsie, it says positive. What did I do wrong? Oh, I changed my problem is what I did. Okay, I changed my problem, so this is not a negative. Did I do something else wrong here? Let me see. No, I'm good. Too bad I did it that way. Oh well, it doesn't matter. 1/4 minus 3/16, that's 4/16. Yeah, we got 1/16, which means that's equal to 0.125. That's our expected value. With these probabilities and these outcomes, if we guess on this problem, or any problem that's like it, we can expect to score on average 0.125 points. Now you're not going to get 1/16 or 0.125 points on any particular problem, but when you add them up and average, you'll get that. Now that tells us something. Does that mean we should guess on problems that we don't know the answer to? It sure does, because on average, we're going to be gaining points. All right. Moving on. All right, here's a table. Let's see. A person is selected from the population described in the table below. Find the probability that the person failed math. I know that you guys are not going to do that. At least I hope not. Failed math, that's what we're looking for. Given that the person is left-handed. Ooh, lefty failures. Okay, what do we got here? Well, we got tables of right-handed, left-handed, and the total, so I guess we just added up each of these. Yes, we did. And they either failed, they scored between 60 and 80%, 80 to 100, and then we added up things this way to get these totals. Question is, we want the probability that a randomly selected person, if they probability that the person who was randomly selected failed math given that they're left-handed. Well, here's the failed math column. Oops, didn't want to do that. Here's the failed math people, and here's the left-handed people. And the intersection is right there. Aha, that's the left-handers who failed, but we want a probability. So we need to use our probability equation, number of favorable outcomes. This time favorable is kind of a weird word, isn't it? Favorable means failed, but think of favorable as the thing you're looking for. And yes, we're looking for the number who failed. So there are 130 people. Get it right, Craig. Eraser, don't kill everything. Pencil, black. There's 130 who were interested. Those are the ones who failed. Oh, I killed everything, didn't I? Yep. The question is, though, failed, left-handed, 130. Which of these totals do I use? Well, let's see. This total is the sum of left-handers and right-handers. That doesn't make sense to me. I'm concerned with left-handed students. Why would I include right-handed handers in there? How about this total down over here? Oh, this is the grand total of all students, left-handed and right-handed in all grades. Doesn't make sense that I would use that. I'm only interested in left-handers, and this one includes both left and right-handers. But there's one other possibility, and that's this one. Let's see, these are all left-handers. That sounds good. And it's the total number of left-handers. There's our number that we want. We want to divide that 130, the number of left-handers who failed, by the total number of left-handers. And that's 2020. And doing that simple math, where did you go? Problem 7. Problem 8, there it is, that's 0.06. 0644 6.44% probability that at Craig's College, if you are a left-hander, you're going to fail, or at least based on past experience, that's what we know. Now, would this be theoretical or empirical data? This would be empirical. It's based on many trials or experiments or observations. All right, we're getting down there. Let's see, what's the next one? Is this the last problem? It is. Okay. One's a little tricky. A lot of people had problems with this one too. The digits 2, 3, 4, 5, 6, 7, 8, and 9 are randomly arranged to form a 3-digit odd number. All right, let's mark this up. There's our digits. randomly arranged to form a 3-digit odd number. Ooh, digits are not repeated. That's important to know. Find the probability that the number is greater than 900. Well, again, we're going to use some form or fashion of my probability expression where in the numerator we'll have the number of favorable outcomes. That's the number of numbers that are greater than 900, 3 digits long and odd, without any repeated digits, over the total number of outcomes. Once again, it turns out the total number of outcomes is the easy part. Total number of outcomes. Let's see, how many digits are there? 2 through 9 is 1, 2, 3, 4, 5, 6, 7, 8 digits. 1, 2, 3, 4, 5, 6, 7, 8. I wrote 9 on my paper. That's not good. 8 digits. And once again, we're forming 3-digit numbers. Let's see, forming 3-digit numbers. Is this like cards where order isn't important? Or is 762 different than 267? Yeah, order is important. Each of those two numbers I just stated are unique. So this time we're looking for permutations of the total number of outcomes. We have 8 digits. We're selecting 3 of them. That's our denominator. Now we got to work on our numerator. All right. So here's our numerator work area. First of all, I want to write down, it turns out that the numerator is going to be an FCP, meaning we'll have the number of ways we can select the first digit times the number of ways we can select the second digit times the number of ways we can select the third digit. Yeah, I'll rewrite that. Number of ways. And we're going to have the first times the second times the third. Okay. And what are our possible choices? I also want to list those. This will make this problem make sense. Possible choices. All right. So once again, we've got our digits, and I'm going to write down my digits, the longhand. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. I'm getting good at counting to 8, aren't I? All right, possible choices. Let's see. That many, that many. No, I didn't want to do that. That's okay. Fancy eraser. Okay, so first of all, it's going to be a 3-digit odd number, and it's going to be greater than 900. Well, there's only one way, one number we can put in to make this 3-digit number greater than 900, right? We got to put our number 9 in there. So this is an odd question, but how many ways can I select the number 9? Again, I'm working on the FCP part. Well, there's only one way I can select the number 9, and there it is. Let's go to the other end. In order to have, my master list. Master list. I'm going to cross off 9 because I've used it. The other end, we're looking for odd numbers, right? The only way a 3-digit number can be odd, or any number can be odd, is we look at the last digit. And it's got to be odd. So there's some choices this time. We could have 3. We could have 5. We could have 7. We could have 9, but we already used it. We can't have 9. So we have 3 choices. Let's see. We could either put in 3. We could put in 5 or 7. And how many choices is that? Well, that's 3 choices. All right, so let's say we used the number 3. Or let's say we used the number 5. Let's cross out 5 because we used it. Now, we still haven't used 3 and 7, but we did have 3 choices there for odd numbers. All right, so we've killed 5. We have, this is too big of a killing. Got to settle down here. There we go. We took out 5, we took out 9, we've used those two. How many choices are left for the middle number? Well, we got 1, 2, 3, 4, 5, 6. We have 6 choices. What are they? 2, 3, because we haven't used it. We used 5 over in that first one, over in that third spot. So we have 2, 3, 4, skip 5. We got 6, 7, and 8. There's our 6 choices. 1, 2, 3, 4, 5, 6. There's our numerator, and that's also our FCP. 1 times 6 times 3. I can choose the first number one way, the second number 6 ways, the third number 3 ways, and now you can kind of see the tree diagram thing going. Yeah, we got that. Then he goes to each of those, and 3 goes to each of those. Yeah, and we multiply those together, and what do we get? There's going to be 18 ways. And that is our numerator. And so now I'll bring our math down below here, our probability math. We have 18 over, let's see, what's 8? Permutation 3, where'd it go? That's 336. And now I can simply write my probability as 0. Do the math, 0.0563. 0.05, nope, nope, nope. 0.0536, thank you. Which, that's a little over a 5% probability. So what is the probability if I randomly choose from 8 numbers 2 through 9 to form a 3-digit number? What's the probability that it's odd, that digits aren't repeated, and that it's greater than 900? Well, I got a 5% chance, about 1 in 20. There we go. That's our last problem, folks. I don't see our timer, how long this video is running, but it's time. We're done. I hope this has been helpful to you. As always, write me, call me. Hey, call me cold or text me, because I won't pick up if I don't recognize the number, but text me and let's talk. I'm always happy to help you out. Thank you, everybody.